One of the most useful nucleophiles that you can add to aldehydes and ketones are called Grignard reagents. They're named after the chemist who discovered and developed them, and actually won a Nobel Prize for having discovered them. And what's key to making them so useful is that they are carbon-carbon bond forming reactions. And that importance of that I know is not necessarily obvious just by saying it, so I'm going to give you an example later on in this module on the synthesis of tamoxifen, which I think will illustrate why these reactions are so useful. For now, we're going to take a look at what they are. So we're used to seeing the carbon atom in organic molecules as being electrophilic because there's quite a few atoms that are common in organic molecules that are more electronegative than carbon, like the halogens or oxygen. And those all polarize that carbon atom so that it's partially positively charged, and so it becomes the electrophile. And so when nucleophiles react, they react at that electrophilic carbon. On the other hand, you can make the carbon atom nucleophilic as long as it's partially negatively charged. So it just has to be bonded to an atom that's less electronegative than carbon, and that's typically metals. So these types of compounds are called organometallic compounds, and they in these organic metallic compounds, because carbon is negatively charged or partially negatively charged, that carbon will react with electrophiles. Organolithium compounds are one example. So the other example here are Grignard reagents. They're organometallic compounds where the metal is magnesium, and they're very easy to make and to handle. You make them simply by using an alkyl halide and adding magnesium metal to it. The ether here is just a solvent, so it's not directly participating in the reaction. And you create, this is the actual Grignard reagent. And the key to them, their carbon-carbon bond forming ability, is that they are sources of carbanions, meaning a negative charge on that carbon atom, right, that's bonded to the magnesium. And since there are so many different carbon atoms that are electrophiles, now if you have a carbon atom that's a nucleophile, you can make carbon-carbon bonds. So here's the mechanism. You don't typically draw it as if that alkyl group, or the carbon on the alkyl group, is a full-blown negative charge. It's usually drawn like this, but what this indicates is that alkyl group uses those electrons in that carbon-magnesium bond to form that new alkyl group carbon bond. Pi bond breaks and electrons go up onto oxygen. And from here you will, in a second step, add acid, and that acid then just protonates the oxygen there, so that your final product here is going to be an alcohol. And then what kind of alcohol is just going to depend on which carbonyl compound you use as your reactant. That is, if it's formaldehyde and you have 2 hydrogens on your carbon, you're going to get a primary alcohol. Let me make sure you follow where that carbon's ending up. So this carbon here, to which this ethyl group is adding, this is the carbon that's negatively charged. That carbon becomes bonded to that carbon, right? So that in this intermediate, there's that carbon, and then in the final product, right, it's that carbon there. So, and if it's a primary, if it's an aldehyde, then when the nucleophile adds, it's going to be secondary alcohol. So this carbon, right, becomes, it's this carbon here. This methyl group here is now bonded to that carbon. And then in the final product, it's that one there. So the carbon that has the alcohol functional group bonded to it, the oxygen of the functional group bonded to it, and the product is the one that started out as your carbonyl carbon. So in this example, we start with a ketone and we add an alkyl group using a Grignard reagent, then our final product, right, is going to be a tertiary alcohol. So yeah, it's that carbon there that becomes the it's that carbon there that's the original carbonyl carbon in the starting ketone. So here's one more example, and I put this one up just to remind myself to tell you that there are lots of different alkyl groups for which you can make the Grignard reagent. So it doesn't have to just be methyl or ethyl. Here's an example where it can be an aromatic ring, a benzene ring. You can make a Grignard reagent of a benzene ring, or pretty much any alkyl group, or aryl group, or vinyl group. So it's a very versatile reaction. And then again, whatever is bonded to that magnesium atom there is what gets added to your carbonyl carbon. So there it's being added to that carbon, and then the product over here, it's that carbon there. And so this is also to remind me to tell you that the reaction may be written like this. So it is two distinct steps. You can't have the acid in there at the same time as your Grignard reagent. So you add the Grignard reagent first, and then the acid to do the final protonation of your oxygen.